I have to stand here. Okay, thank you. So I'm going to talk about the development of the system behind this gentleman's device. It's a next generation Parkinson's system that basically responds to his brain rhythms in real time and makes adjustments to the stimulator. But I don't want to dwell too much on the specifics of this case. In light of the conference, I actually want to also really focus on the standards and the risk mitigations that are implicit, and I want to make them explicit in the design of this system by telling you sort of the story behind some of the technology. I won't say failures, but observations that we made deploying and getting it into the clinic. So just to get started, no laser pointer, but this is an example of the burden of neurological disorders, and this is just a snapshot in the EU alone. The top row is the number of millions of people in a given year suffering from the disorder, and you can see it going from brain tumors all the way up to 60 million plus people with anxiety disorders. The middle row is the cost to treat one of these individuals in euros, and then the final row is the aggregate costs. So you can see many disorders today, such as dementia or mood disorders, which is depression, are 100 billion plus within the EU. And technology today, we're really focused on brain implants and treating Parkinson's disease. So one of the things I'm interested in is what can we do to better treat Parkinson's disease patients, but also think about how we can map the same technology out, as Amy was saying, as a platform to treat these other disorders. Now, especially for the students, you might think neurological disorders, why not go to pharma? First stop, especially we're here in the Cambridge area. Where's pharma today? So this is a plot from an analysis in Nature about a decade ago. The y-axis is logarithmic, please note, and this is the number of drugs released for $1 billion if you invest, U.S. investment, inflation corrected, and then the x-axis is time. So you can see a trend, and it's not a good trend. In fact, pharma people call it E-Room's law. I did not come up with that. They're making fun of themselves. And actually, The Economist just came up with an update of this. So the slope has actually shallowed out a little bit, but it's still showing the same general trend. And so this, of course, E-Room's law observation. Pharma is in direct opposition to Moore's law. So this is also courtesy of IMEC. This is a chip from basically the year I was born for the students, and this is how that same chip would have scaled over time. It's not that they stopped innovating, as you just heard, in 2014. It's that it no longer fits on a pixel, so they couldn't draw it anymore. It's just, there's nothing, it's sub-pixel. And so, in my area, we think about what can we do to apply Moore's law and bring it into this space of medicine. And so the vision in the lab, and also in my spin out, thinking about devices that are truly restorative of physiology. And so physiology has both feed forward, and so I have circadian rhythm disorder right now because I just flew in from London yesterday. So think of that red eye, so you have these natural rhythms, that's kind of a feed forward process, and then it has feedback mechanisms. And so in reality, physiology balances both of those to optimize control, and we're thinking about building devices that do the same thing, applying both feed forward, but also feedback. So this requires new sensors and their application. And that's what I'll talk about, an example for the rest of this talk. So that's our vision, and this is actually building a bit on Amy's point, is how do you actually execute? And so one of our challenges has been, in the case of medical devices, where it's $50 to $100 million of investment for a new system to prove out new concepts. And so behind the scenes, and what I'm going to talk about, was actually a research device that instrumented a brain system with new sensors, so bioelectric sensors, inertial sensors, algorithm capability, and then in combination with the Brain Initiative, kicked off by Obama and then followed on with the NIH, we actually ran about 25 clinical studies. And that's actually what's behind the scenes of what I'm going to show you, some snapshots from that data. And that really helps to deal with the regulatory pathways, some of the workflows and the like, and de-risk those and show that we actually have a mature technology. So where were we? Kind of snapshot of 2020. This is an example of a gentleman with intention tremor. So for the engineers in the audience, you can think about it like he doesn't have enough phase margin in his control system. So he goes about his activities of daily living, such as drawing a spiral and writing or holding a glass of water. The more he tries to focus on motor control, the more unstable he gets. And so what's happening is on the left-hand side, his device is turned off, and on the right-hand side, his device is actually turned on. And so what is actually in his body is basically something very similar to a cardiac pacemaker. So it has a battery source, electronics that give a fixed rate of stimulation. Electrodes are routed up through his neck, and then a stereotactic neurosurgeon places the electrodes into specific targets. So depending on the brain disorder we're trying to treat, the surgeon will put those into different locations. So in this case, this is in the thalamus to treat and the essential tremor. Now we got started by thinking about reversible lesions. So historically, neurosurgeons would actually go in and actually just cauterize the tissue. So they won't teach this at Harvard Business or Harvard Medical School, but we say, bad brain is worse than no brain in many disorders. And so they'll actually destroy that part of the brain in order to treat symptoms. And so it anchored the field, this idea of reversible lesions, because that's a bit of a static concept. And so kind of that classic 1990s until basically now, we were really working on what we call, brought up earlier today, the human in the loop. So I say it's a manual loop because there's no such thing as an open loop device. That would be you get your implant, you walk out of the clinic, and good luck. In reality, every 3 months, the patients return. Perhaps the most undersampled process in a feedback loop in medicine, you kind of ask, how have you been? And the patients self-report, you take a few observations, then the clinician does a manual adjustment to the stimulator, and then they're out for another 3 months. So that's been the classic kind of treatment paradigm. And where we're going into 2025 now is a new generation of more automated neuromodulation therapies, where there's still a human in the loop, that's a clinician, but they're actually setting up the classifiers. So just like setting up a thermostat, where they're going to look for physiologic control parameters, that's oftentimes reflected in the brain's rhythms. Then they compare those rhythms to a set point, and then the algorithm automatically makes the adjustment. And then once again, there's feed-forward elements, which I'll talk about, like circadian rhythms and why those are important to consider as well. So this is where we want to go, and where we're actively working in the space, both our lab, but industry, and in collaboration. But when you think about that step from a clinician in the loop to adjusting a system to a more automated closed-loop system, it really brings up new questions and risks that need to be addressed. So what are the nature of the input signals, the biomarkers? What are artifacts going to do? Is the set point stable? What are safe actuator adjustments? And what are the fallback modes that we need to place? So I'm going to go back and walk you through this example. This is the original concept behind that Parkinson's device. And this is how it works. Think about a home thermostat. If you understand your home thermostat, you can build a brain implant. So the mental model is that there's this rhythm at 20 hertz. Sorry, I'm stepping out of the ring, but 20 hertz. And so these are being measured off of those electrodes in the brain. And these correlate. The higher the energy in that spectral band, the more the Parkinson's patient is showing their symptoms. So we can measure that energy off the electrodes, set a threshold algorithm, say when you cross that, just like a home thermostat, we're going to turn on the stimulation. When you fall below it, we know you're asymptomatic, so we can turn the stimulation down. And what was exciting, this is actually 20 years ago, was that the pilot tests in the clinic were showing that we had an improved clinical outcome in about half the energy use. And now that you may say, who cares about half the energy use? Sustainability. These are primary cell devices. So by avoiding an implant, doubling the time between implants, you save the healthcare system $25,000, and you save the patient a surgery. So it actually has very tangible economic benefits to do this. So that's great. Let's go. So what's been going on for 20 years? That's like my old executives at Medtronic would say, what's taking so long? So let's go step through these risks and some of the questions. So first, the input signal. Those brain rhythm signals are on the order of a microvolt RMS, so about 1,000 times smaller than a cardiac pacemaker. And so getting a microvolt level measurement chronically off of the implanted electrodes is quite a challenge. We were not as worried about invasiveness because we're already putting a hole in the skull and placing the electrodes deep into the target. So the invasiveness wasn't our big question. It was, can we actually get a robust microvolt level signal 24 hours a day, 7 days a week, especially in a home environment? The other thing in terms of the biomarkers, understanding it. So what's the transfer function? Just like in engineering control, what's our transfer function between stimulation or pharma and the biomarker of interest? And so right around the turn of the millennium, there was a look at that 20 hertz marker, and they saw that it would actually correlate with the symptoms and also how those symptoms changed in the presence of dopamine, so synthetic dopamine given as a pharmacological agent, and that's on the left. And then on the right, looking at the frequency change, kind of that beta activity, as we staircase step up the stimulation. The red bars are where the patients are asymptomatic. We saw a similar response to pharma. So this is actually an advantage. So pharma goes slowly, waxes and wanes. The stimulation we can adjust on a second-to-second basis. And so there's a nice complement here between electrical stimulation and the physiomarker of interest. So that's great. So far, so good. We have the technology to measure microvolts. We have an understanding of our transfer function. So what could go wrong? So notice, where are we putting the implantable pulse generator? Right over the heart with this 1,000 times larger signal. So instrumentation problem, common mode rejection ratio, leads basically are mismatched, these kind of polymer coated metal electrodes. Getting 60 to 80 dB of common mode rejection ratio is a real challenge. And so the issue is that the peak of the QRS cardiac signal is right overlapping with our signal of interest in this beta rhythm at 20 hertz. And so when the devices were first deployed, about half the patients were actually getting corrupted signals from their heart. So one of the things you do is you ask the surgeons, what side of the chest are you implanting it on? Half of them on the left side, we'll move it to your right. Drops the signal by the artifact by about a factor of 4, and that deals with it in many cases. Then our own research is putting the entire device up on the skull. So some of these practical things of where the surgeons place the device really can have pragmatic inputs on or impacts on the way that the closed loop system is going to operate. So that's an artifact from the body. The other one is stimulation. So just like you're building a radio with trying to do full duplex operation where the transmitter is, say, 1,000,000 times more powerful than the receiver signal, we have the same issue here. The stimulation is putting volts across the tissue. We're trying to measure microvolts. And if we zoom in on this, we can say, this was with an ideal amplifier, kilowatt in the lab. Well, in reality, when we turn the stimulation on and off, it creates this broad spectral kind of artifact, which when it runs through the classifier, glitches it, which says, oh, I turned off the stim, but now I'm actually getting my physiomarker back. I need to turn stimulation back on. So it turns on, then you say, oh, artifact settles out. No, I don't need stimulation on. Let me turn stim off again. Nope. Go back to the artifact. And so all of a sudden you have this relaxation oscillator built up by this sense-stim interaction. It has nothing to do with the physiology of the patient. It's all driven by the stimulation artifact coupling. And patients don't like this. They'll say, turn it off now. And so we had to deal about these artifacts. There's also physiological responses that can create relaxation oscillators. So some of these dynamics and the interplay between stimulation and what we're sensing were also crucial to work through and thinking about interlocks in the system. Now, one of my favorite conversations with the regulators was after we'd worked through everything so far, I said, I think we're done. The Brain Initiative, the trials have shown that we have a pretty compelling closed-loop system. We can map it to the transfer functions, understood. And they said, no, you've never characterized what the algorithm does when someone's sleeping at night, let alone taking a nap. So in these new generation devices, we can actually measure the average activity in the brain for extended time. So this is actually 1 month of activity. What we're doing here is capturing every 10 minutes. We look at that power and the beta rhythm of interest and record it and store it in the device. And do you notice a certain trend? for students. Any trend you see? There's 7 little divots in a given week, and that's actually at night. So when the patient's going to sleep, this beta signal is actually going down. And so our simple algorithm would say beta's down, turn the stimulator off, but we know from clinical experience that they prefer their stimulation to be on. So at night, the algorithm would actually be doing exactly the wrong thing. And so this is something we have to account for. So thinking about the sensor design, I don't know about your sensors, but certainly any physiological sensor, thinking about circadian rhythms and how do those need to be accounted for has become really front and center in the work we do. And so one thing that I'll just say as an aside, being very pragmatic, like I'm an engineer's engineer, even though I'm a professor, is that when I look back, I go, why didn't we do the easy thing first? 50% of the variance in the beta rhythm and these symptoms is simply the time of day. So we spent 100 million plus to build a new closed loop stimulator, run clinical trials. A real-time clock costs about $1. And also in terms of, we call it the diffusion of innovation, customer acceptance, clinicians understand daytime, nighttime, and how to set the microwave and set a clock. We didn't do the easy thing first. So it's lesson learned. If you have an easy solution that accounts for half of your variance in your problem, solve it the easy way first. You don't have to do it the hard way. Then the last point on this is homeostasis and algorithms. So we started out with this bang-bang controller, kind of all on, all off. There's no physiological process that kind of operates that way. It's more, physiology, even going back to Walter Cannon, the great, original, explorer of homeostasis, said the physiology tends to have guardrails. You kind of let the body wander, these processes wander, and if you go a little too high, then you take action. You go a little too low, then you take action. And so one of the things that was an outcome of the BRAIN initiative was a researcher at Stanford, Helen Bronte Stewart, explored doing the control algorithm not as a bang-bang controller, all on or all off, but more like a homeostatic response. And what's interesting is in the ultimate clinical trial was this homeostatic algorithm that outperformed and met clinical significance and statistical significance, not the original bang-bang controller. So it's a bit to Amy's point of you have to do discovery and not assume you've got it. Kind of this took 10 years to dial in and get right. Now the last point, and I'll close out on this though, is thinking behind the scenes, all the safety in the automated systems, and thinking carefully about how can it go wrong. When we have an adaptive algorithm, what are the considerations that we need to bring into place, understand the dynamics. And I think it's really relevant. Lessons learned here can apply to all the sensors, from cruise control to air flight control. And this is where, if you're interested in sensors being embedded in a system, this is a great regulation from the FDA. And just forget about it being about physiologic control. Just think about any control. As they step through systematically what was behind the basis between closed-loop anesthesia systems, the artificial pancreas. These were the motivations for these applications. But they said, as a general standard, what are the things that a designer needs to think about carefully to come up with a safe and effective solution? And so this is where I think they're a little bit precious, use an English expression about how they define physiologic control. They're very explicit. I'm actually arguing with them a bit about being so explicit, but it does map into the classical control loop that we'd all expect, including disturbances. And disturbances would be like patients taking their medication or going to sleep and the like. But this is the key, is that there's a whole framework of thinking about how we build up a closed loop system. So this is mapping it into regulatory speak, where the blue boxes are the classical closed loop system. We have the patient as the transfer function. We have the sensors as the measuring transfer element. Comparison and control is the classifier and control policy, and then the actuator. And then the clinician is the command transfer element who configures the algorithm to run. But critically, there's these tan boxes. So the mental model of operation. So you hear me talking about a thermostat. That's so we have a common language talking to clinicians about how to think about setting up and debugging the algorithm. Physiological dynamics. Are there any delays in the system? You know, one of the classic ones is how does the body respond to stimulation and maybe suppress algorithms? We talked about circadian rhythms. That's another consideration. So do you understand the dynamics? The ones that are critical are fallback modes. So if something should go wrong, what is the action that the clinician or the patient needs to take? And so patients are all walking around with a little controller about the size of this system. And if for some reason they don't like the algorithm, they can immediately turn it off and it goes into a predefined safe operating zone. So basically open loop, that open loop stimulation that they're used to. And then also actuation limits. So we don't want to turn the stimulation up too high, it can create side effects, but also we don't want to turn it down too low because they might lose their therapy, and that means they might actually become akinetic, trip down the stairs. You know, we want to think about what are the lower limits as well as the upper limits. Additional topics that really, when I teach this to students, we go through the 737 MAX as an example and read the case story. Send me the 5 minute. Okay, so the PCLC, automated flight control, other elements that are relevant from avionics to medical devices to automated to autopilots in cars. So automation bias, we heard about it earlier. Clinicians tend to be very trusting of an algorithm. And so, Amy talked about the mistakes that can be made. Do we trust those algorithms too much? And then think about complacency. If they think the algorithm's doing the job, maybe they're not going to pay as much attention as they should. Big one is entrance and exit criteria. It's like on the 737 MAX, knowing how to disable the automatic control algorithm. Same thing for our medical devices. When it's going awry, do you actually know how to turn the system off? And also when we turn it on, how long do we let things settle before we actually let the loop take over? We tend to have kind of a soft start, not just turn it on, and part of that is because the amplifiers have to settle out, the classifiers have to establish themselves, thinking very carefully about that. And then of course, loss of situational awareness and skill degradation. As we automate more and more of these systems, if for some reason you have to revert back to classical methods, do our practitioners actually remember what to do? So just to wrap, is that the story is between that initial pilot experiment 20 years ago. There are a lot of activities, including several. We went through 2 generations of research prototypes before we got the final product in place. But that helped us to resolve all of these issues systematically. And all this is, of course, to enable future vision of more automated systems that restore physiology. But I hope the take-home points about risk mitigations and thinking about actions can actually resonate across all of your different applications. I'm happy to talk about them today. Thank you.